Okay, we should be on. Welcome everyone to the Journal of Gemology webinar through the Gemmological Association of Great Britain. It's great to have you with us today. I'm pleased to say we're once again joined by Brendan Laws, the editorial chief. There he is. Hi, Brendan.
Hello.
You okay?
Hello. Nice to be here. Yeah.
Good, yeah. So as usual, everyone is on auto mute, so your webcams are off and only people here can see our panelists. But any questions or technical issues, you can, of course, submit those in the chat function. So just a quick recap, Journal was first released in 1947, our Journal of Gemmology. It's a recognised leader in this field and publishes original research on gemmological research and articles, things like natural stones, treatments, synthetics, simulated gemstones. We have gem notes, we have feature articles, news and conference, and of course, learning opportunities and links. And it also has this SCIE, the Science Citation Index expanded. We're very pleased that it's a peer-reviewed. It's one of 9,200 journals that are across 178 disciplines. So it really does put the science and the subject of gemology on the map, so as to speak. And it's highly prestigious. And we thank all our authors and, of course, our people for their contributions. We must say it's published in collaboration with the SSEF, the Swiss Gemmological Laboratory, and with the support from the American Gem Labs, the AGL. And the journal is on our website under membership and all journals, and it's there for you to read alongside the archive. Now, today you can see our front cover, a lovely front cover on emeralds from Panjshir. We did try to get Michael from the SSEF with us today, but he couldn't make it. But we did record a video yesterday with an interview about this fantastic article. So what we're going to do now, the first start of this webinar is to just show you that video. Then after that, we'll come back and we'll go through some highlights. Okay. Hello, everyone, and we're really pleased today to be joined by Michael Gemology and Heo Wang from the SSEF Labs. They're going to give us an overview about their beautiful new paper, a new type of emerald from Afghanistan's Panjshir Valley. How did you come to write this paper, you two guys?
Good question. I mean, this material came to the lab and it was the stunning effect to see such a quality of stones. And it was also from the curiosity because we saw that this material is somehow similar to Columbian, but still different. So this is where it started to do research. And when we had the facts together, we decided this is something we need to make accessible to people and other labs also. And that's the reason behind it.
Wow, so you know, as you read the paper, it says there that some of these new stones have such a high quality that their reputation is selling equivalents to some classic Columbian material. Yes, that's right.
Yeah, I mean, in some aspects, these materials are, at least what we have seen, in quality superior to many stones we see from Colombia, because they have quite often very little amount of inclusions. So this material was really stunning from the beginning, and consistently we had this high quality. I cannot comment if all this material is of this high quality, because we see at the lab quite a selection of the high-end quality always.
Can you talk a little bit about when the material came out and any idea of the quantity?
Well, what we can say is when we first saw this material, so this was in 2017 when this material came, like quite often during a gem show. I mean, the gem show is the moment when new material is presented to the market, and as we are present there to test stones, we see then quite early this material. So that was the moment when we saw it first. And so it's not just coming from, let's say, 6 months ago, but it has a certain history already. And in quantity, that's not so easy to say also, because I mean, we see a selection only, and I guess only the high quality section, but it's common in like quantities which are reasonable. I mean, we talk about 50 stones, 20 stones. So we see these kind of lots coming of stones. but definitely it's much less than Columbian stones.
Maybe
Now,
we
I
can,
do love this first image here, where you got the three stones. Of course, you separated them from sort of, I suppose, the earlier finds on the left. That's quite a quality stone. Then the newer type in the middle, the Panjshir 2, you're calling it, and then more established Langham emeralds as well from Afghanistan. I think it's great that you can actually see the difference, not only in the quality but also the subtle hue variations, can't you?
Yeah.
So yeah, it's just to give you an idea where they occur. I love seeing maps like this. Just this Panjshir Valley. I think it's the Valley of the Five Lions. You said it was equates to, and it's always good to have the location map. That may look like a relatively small area. It's quite a large area of this map. And what I really liked about this paper is that you've gone straight to the microscope as well as your first look at these. It's classic gemology, isn't it?
Absolutely. I think this, I have to say, is the beauty also of our work. I mean, this classic aspect of looking into the stone is still nowadays so important. I mean, the rest of the article shows data and visualization of the data, but still we can read out with the microscope, we can see so many subtle differences, and it remains to me the most important up to nowadays. And that's why we try to show characteristic features so that even a normal gemologist with a good microscope can have quite a deep understanding of this material. What we see here are starting from inclusions which are typically also described in literature, like fluid inclusions, which are present, which have a similarity actually to Columbian fluid inclusions. So we have these spiky jagged inclusions which are multi-phase. Then we go into zoning effects. We see a zoning in figure number D, and we then come to channel structures, which are actually a quite common structure in all beryls, and whether it's now an emerald or aquamarine, whatever. But we see there is a certain, let's say, size and also thickness of these channel structures in this type 1 material. We also see then solid inclusions, which are typical. And so the idea is to give a brief overview on all types of inclusions, also corrosion features, iron hydroxide, and these corrosion features, which you also see in a faceted stone then. So that's to give you a certain overview about the range of inclusions.
we should mention here that this is the original Panjshir material that we're looking at now, not the new material.
Absolutely, yes.
Next slide is the new material.
Yeah.
I was quite taken by this fluid inclusion with these sawtooth edges, which I think you said is distinctive for these new type, yeah?
Yes, absolutely. I mean, that's what we have seen. This is something which is beyond the normal kind of jagged, or we call it spiky fluid inclusions. This is really this micro sawtooth pattern, which we have seen now in this material specifically. And yes, it's very astonishing and aesthetic, I could say. I mean, these inclusions are also these hollow channels, which you see, for example, in the figure number I. And this is really a very beautiful pattern. So apart from the inclusions here, I think also what you see from these photos is that these stones are very pure actually. So you have this, let's say, these hollow channels, but you don't have a lot of other inclusions surrounding this. And you have also the reddish fluorescence, which you can already see by a fiber optic lamp, which comes then in the figure H. So yes, it is different, and that's the importance then for microscopy. It's really different to what we have seen in the classic, or let's say Panjshir type 1 material. So somebody looking at this carefully should be able to spot and to make the difference between the type 1 and type 2 material just by comparing with these photos. what we try to present here are all the different aspects you can analyze on the stone, and where you can work to check whether you have a difference between different sources. And one important part is for sure the absorption spectroscopy, which actually shows you finally the elements which are responsible for the color. And what we see here is that there are differences between the different types. Only if we talk now first on stones from Afghanistan. So we have this Lachman type, which is basically similar to what we would expect from a stone from any kind of a microschist deposit like Zambian or Brazilian stones. So you have specifically this iron band in the near infrared, and you see how this is getting lower and lower. And on the right side, you see then also when we expand and we have a look into Colombian stone, which is important to be able to separate from this new material, then in fact this new type is quite similar to, or most similar to Colombian stones. I mean, this is also a reason why some of these stones were misinterpreted first as Colombian, for sure, because they are so close some point in inclusions, but also in analytical properties. Expanded to other techniques like Raman, where you have a look on the position of the water molecule in the channel structure, where you can compare again different origins, and you see again that this is finally helpful. And we talk here from the side of origin determination as a lab, and we try to present all criteria so that even other people are able to understand and follow this.
Yeah, I think that's. I think what I really loved about this paper also was the sort of the journey you took us through from the very beginning. You had the problem, and then you went straight into the sort of gemology. Then you threw the analytics at it, and sort of like a detective, you slowly worked your way through the system. Then you could separate, you know, Panchia 1 from Panchia 2, for Blackman, and then through Colombia, and then refer it to all the other gem deposits that we know of, you know, like the Mathics, the Russians, the Ultra Basics, the South Africans, for the geological setting. I thought it was brilliant.
Can you guys tell us what you did here with the trace element data?
Yes, so this figure is generated based on a GEMTOF instrument at SSEF. So GEMTOF is one of the advanced analytical instrument at SSEF. It measures nearly all the elements from the periodic table from the emerald samples. So in this case, we just show some elements which are measured and plotted them in a 2D or 3D plot. But actually, we have constantly monitoring more than 50 elements at the same time from emerald. So this technique is capable of measuring a large quantity of elements. At the same time, it also measures elements in a very low concentration. So we are talking about not only the major compositions of emerald, or even minor compositions or trace or ultra trace concentrations of elements are constantly quantified. We did the measurement in a way that we just measure whatever possible that we can detect from emerald, and then we make quantification and selection and based on the experience, and to see which elements are important for emerald, and then we make this plot. There are some characteristic plots which could hopefully give some ideas about the origin determination, the separation.
Maybe I can add from my side on this. I mean, this is more the classical approach. What we see here is how chemical data is normally displayed. So you can use a 2 or 3D pattern, and you try to find like relationships and clustering, and you try to visualize the data. Now, we are somehow limited in dimensions as a human being. So 3 dimension we can handle, and we have even some kind of like a movie, which is in the paper in the data depository to be viewed. But at some point we get limited. To see the full context of all relationships, we would have to produce 100 plots. And that's where also then the work comes, which Hao has done a lot, where we use statistics algorithm to reduce actually this high dimensional data set.
This is a straight element plot.
A classic way to present 3 elements and to see, oh yes, they cluster. So it's already very valuable because we can sort out different origins, and this is specifically for separating DAFDAR, which is also quite close in many aspects. But this is rather a classical aspect. But what we see here, I would say important is these elements you can reasonably detect only by using mass spectrometry. I mean, nickel amount is very low, rubidium and cesium a little bit higher. So with an X-ray fluorescence, for example, you would not be able to produce such a plot.
And this is similar as well, isn't it? I think, yeah, including both Colombia, Ethiopia, Nigeria, Pakistan, and Zambia.
And what we see here actually is we can cluster different origins, but we see also quite an overlapping pattern. And this is the problem, because actually now when we have a data point which is in this rather mixed zone where you have different origins overlapping, we still would like to kind of extract the information where it comes from. So we see by using this rather classical approach of just plotting different chemical elements, we will not resolve this problem. So we'll have to go a step further.
Yeah, this Disney plot is kind of a machine learning algorithm that basically projects 56 dimension space, basically 56 elements down to a 3-dimensional space. So then in this way, we would be able to resolve or visualize the relationship of different data points, how close they are from the 56 dimension, which for human being, we are unable to see that, down to a 3-dimensional space, which we can see. So in this way, we can plot the data after this projection or dimension reduction, and then visualize that in 3D and present to our gemologists. So in this way, they could see a new stone coming in and relatively comparing to other gemstones from the database, and see which gemstone is close in terms of chemical elements, chemical composition. And if you, I mean, you could imagine that if we're talking about here more than 50 elements, and if more than 50 elements are very similar comparably, then there is a highly chance that they may come from the similar geological environment, therefore a similar origin or country of origin. So that's the idea behind that.
I think, yes, when you go through the paper, this figure 20, which is the last actually, is actually some kind of a key figure, because the clouds and also the points, which are here quite mixed to some extent, I mean, Ethiopia and Zambia, just to name 2 of them, can be much better separated. The point is that when the data is integrated or is used for these calculations, we don't label it beforehand. We don't say this is now Colombian stones and this is Zambian stones, but we just give the data to this algorithm, and he clusters the data first, and only afterwards we check and we see, now this cluster is fitting to this origin.
Yeah. Yeah. So in this way, we are not really biased by the information, a priori information given from maybe from a dealer or from the market, because somehow the information may be not certain, or you cannot say 100% sure. So that's why we first cluster them, make the difference, then we try to find out information which can give us a second proof, therefore improving the confidence of the origin determination.
It's a very powerful technique.
But you know, as Brendan said, it is a really powerful technique, and I was wondering, are you going to use this elsewhere on any other sort of groups Is it feasible to do that?
Yes, it is. I mean, whether we use now our GemTOF or whether you use a laser ablation instrument, which is a traditional quadrupole, doesn't matter so much. It's just finally the question how you select the isotopes or elements. If you select this more or less the same, you can achieve a similar data set and go through the same kind of algorithms. Something which, that's the reason also to present it quite detailed, is that others can kind of follow and understand. So we don't want to hide them.
Yeah.
I guess you've got another paper you just published that goes into this in more detail.
Yes, so there's another paper published just recently on the Journal of JAS, so-called JAS, JAAS, from Royal Society of Chemistry. And this paper discussed the details about how we did the measurement, how we did the Disney plot, the machine learning algorithm. So I think that's, if one is interested, there are more information over there.
I mean, from my side, I can say this paper gives like both sides some information. Even, as I said, well-trained FGA gemologist with he was used to use a microscope, he will catch already quite important information and can make a lot of distinctions. But then the second layer is the layer for, and that's science. Then this is a layer for scientific gemology where you can use the data, the trace element data mainly, or the Raman data, and you go deeper into it. So it covers kind of both sides.
Yeah, and what I love about the paper also, the TOF analysis, you get the whole periodic table. You still got to look at each one of those elements to decide which one you're interested in to do your distinguishing. And so I think sometimes we think that machines are the be-all and end-all of it, but it really is always down to the interpretation and the well-rounded knowledge of the gemologist looking at this stuff itself. And I think the way you presented the paper, I mean, Brenda and I had a chat about it, and we think it's one of the best papers we've seen, you know, in terms of subject matter, great gemology, good outcome, you're fixing a problem, and there's something for the future going forward that can be applied gemology. So no, congratulations. It's really, really excellent.
Thank you.
Okay, looks like we're back.
So yes, Brendan, can you hear me?
Yep. Can you hear me?
Yeah, definitely. So that was a really good chat we had yesterday about this great paper.
Good detail.
Okay, let's move on. Should we go to the what do we have? So yeah, this the discovery and naming of Alexandria. Now this paper by Carl Smetzer. This was a long read, but you know, actually a really interesting read. What did you think of it, Brendan?
Yeah, there's a lot of detail in this article too. It talks a lot about history of an interesting chapter in mineralogy that most people probably don't know about. And that is the discovery and naming of two different gem mineral or gem varieties that occurred back in the early 1830s.
Yeah, that's right. We all know of Alexandria itself, the famous discovery, but of course not many people may realize that at the same time, actually, right at the same time was Phenokite.
That's right, both in the same area too.
Yeah, both in the same area. And this guy, Kokovin, he was director of the Ekaterinburg lapidary works. It seemed that the material originally came through him, and then he farmed it out to all of these separate researchers, and they had quite a time deciding who's going to get to publish.
Yeah, and also who's going to describe it first, and who's going to name the mineral or the variety. So yeah. On the next slide, we'll see where this is all taking place. This is in Russia's Ural Mountains, and in that area, this is an old map from the 1850s. You can see there's several different mines where they were exploiting emeralds, but they were also getting phenokite and chrysoberyl, especially alexandrite, as byproducts of mining for the emeralds. And here are the names of some of these mines in this area. They're all hosted by a talc and mica schist unit that's surrounded by granite. where the mineralization took place.
Yeah, and Kokovin, I read in his paper there that he worked in a Stratensky mine mainly,
Right.
and he was collecting specimens from there. But there was quite an intrigue about him, wasn't there? That he was sort of said to have stolen a few emeralds. So it was quite an investigation into his house and where these emeralds might have disappeared from.
Yeah, it's another side story on itself that in 1835 he was accused of stealing emeralds and other valuable gems, and this occurred at the same time that the mining production had gone way down, and so it's not really clear as to whether he was really stealing or if he was being framed for other reasons, or if it's just because they needed a scapegoat, if you will, for the mining production that was going down. And plus, he had had a falling out with one of the leading government ministers who he was working with during this whole time. And as a result, that might have not helped his position at all. So,
sure.
So we'll go to the next slide. This is what they were looking for, the emeralds there in the Ural Mountains, both as specimens and also some beautiful cut stone material. And the next slide. And the phenokite was, this was a new mineral that was both a new mineral and a new gem, which is pretty unusual. And that came out at the same time. They initially thought, because of its resemblance to quartz, they didn't realize what they were dealing with, but it took some studies of the morphology and other properties to recognize that they were dealing with a new mineral here. And that's when a big scramble came to characterize and name the new mineral. And initially, the mineral was actually called Kokovinite, after Kokovin, who was in charge of the mining and production of the Ural emerald mines during this time. And but subsequently, when it was being described by the mineralogists, they actually systematically ignored that name and named it phenokite after the Greek name for, I believe it's like an impersonator or something, which means, which alludes to its resemblance to quartz.
That's right, and in the paper there's some original descriptions about this material, like even looking like calcite from Freiburg. They didn't know what it was till they did the analysis, you know, and they did find out it's a beryllium silicate, which is quite an unusual mineral in itself, as to occur in such large sizes. And there's a great rush, wasn't there, to get this thing named and classified.
Yeah.
What I love about the paper is we've got the next slide with all the people that were involved. So you can see Kokovin was the man. Then he sent it to Perovsky, von Werth, Berzelius, Nulinskild, Rose, and they've all got minerals named after them, by the way, which is quite fun. And of course Brewster down the end there, who was the father of modern optics. He was the one that named Alexandria after cymophane. He called it a variety of cymophane rather than chrysoberyl. But yeah, and when you look at this paper, there was massive insights really into the workings of the founders of mineralogy at that time, and the element of competition, isn't it? They're all competitive, and the intrigue surrounding, once you get the stuff, you want it to yourself and you want to publish it.
And if you're a mineral collector yourself, you want the best specimens.
Yeah, absolutely. Yeah, not much has changed really, is it really? Today? But there you go. Okay, yeah, brilliant paper. So we move on to the color change enhancement. So the enhancement of pink tourmaline from Nigeria by electron beam and gamma irradiation. This is a really interesting paper as well.
Yeah, this paper is documenting the irradiation treatment of pink tourmaline, which has been known for quite a long time, but in this case, the authors are focusing on material from a single locality in Nigeria, and they're also looking at a comparison of two different techniques for irradiating it to see, with the same dosages, which one might be more effective or how they might be different in the results that you obtain. So we'll see in the next slide what they started with was a variety of color, ranging from very pale to somewhat dark already before treatment. And they cut each sample into blocks that they could then orient relative to the C-axis for spectroscopy and for color observation, because of course tourmaline is a very pleochroic mineral. They analyzed all the stones and found that they are indeed Albite, which is the most common gem variety of tourmaline. And that's the plot on the right there, showing that they plot near the apex of the alkali group there, meaning that they're very sodic rich, typical of Albite. Next slide. And then after treatment, this is what happened. So the sample, there are 4 samples shown on the left, and for each sample on the left column is how it appeared before treatment. And then as you go to the right, you have increasing doses of radiation from 400 to 1200 kilograys. KGY is kilogray, which is a measure of irradiation dose. And the top, for each sample, the top row is the electron beam results, and the bottom row are the gamma ray results. And if you look carefully, you'll see that you get slightly deeper colors with the electron beam as opposed to gamma rays. And this is interesting in and of itself, although electron beams are typically not used as often for gemstone irradiation, with a few exceptions like topaz, because you do have a problem with residual radioactivity with electron beam irradiation sometimes, whereas with gamma rays, you don't have that issue. In this case, because such low doses were used of the electron beam, you didn't have any problem with the residual radiation. So on the right-hand side are the UV-vis spectra that were taken in this orientation of all these samples. And the main thing to take away from this is that the bottom line, the one that's closest to the x-axis there, the blue line, is the sample before treatment. And then after treatment, you have these distinct peaks that developed as a result of the irradiation treatment knocking an electron out of the manganese ion and causing it to go from manganese 2+ to manganese 3+. And manganese 3+ is a much stronger chromophore than manganese 2+ in tourmaline, and as a result, you get the pink color that forms after irradiation. In most cases, that's the case. Now for the bottom sample, you'll see there's actually some yellow coloration. And this also occurs sometimes in tourmaline when it's been irradiated. As you can see, it started out very pale, colorless, near colorless material, but it didn't have much manganese in it to begin with. And when it was irradiated, it turned more of this yellow color. And that's probably, they think, a result of hole centers that are forming in the tourmaline as a result of the irradiation process. Not a lot to see on the spectrum here. The manganese 3+ features are very small as a result. It looks like we might be having problems with, there, your camera's back on now, so that's good.
It's fine. Get
Okay.
on back again.
Okay, great. So that's really what I wanted to say about this slide. We can continue to move on to the next article.
Yeah, now this is an intriguing one. This is a diamond, revealing formations of a name, the Matryoshka diamond. Really interesting. We've known about this diamond before, but it's, you know, it's you look at that. There's actually 2 diamonds. So when you rotate this, the one in the center you can just see moves. So it's a diamond grown within a diamond. And this paper was looking at the mechanism why. And the mechanism of formation of it and the sequence of events that made this material.
So this is a really rare example of a diamond inclusion within a diamond that actually is mobile, so that it moves around when you move the diamond. And in the original GIA description of this diamond, they did postulate an idea that this could have formed as a result of selective etching of the diamond before it was, came up and was erupted onto the Earth's surface. And in this case, Emanuel Fritsch looked at the literature of diamond resorption and also some other examples of diamonds that he has seen that are both zoned and resorbed in specific ways in order to kind of drill down a little bit better on the history of how this diamond might have actually formed. So in the next slide, we'll see a very useful diagram that he prepared showing how we think this happened, where the diamond originally crystallized starting from the core outward. It had typical octahedral growth, which was gem diamond growth. And then that growth sequence was interrupted by a period of fibrous growth, which was then subsequently overgrown by another layer of octahedral growth. So that's what the O, F, and the O stand for. And at the same time, you had some dislocations, which are growth interruptions that commonly they're called screw dislocations that extend all the way to the surface from this intermediate fibrous zone. And what they found is, from previous research, is that diamond is preferentially etched along these dislocations much, much faster than in areas that don't have the dislocations. So the resorbing solutions came in along those dislocations and actually caused channels that penetrated clear into the fibrous zone. And once the resorbing solutions reached the fibrous zone, because of the structure of that zone having a lot more surface area and a lot more inclusions and irregularities, that was preferentially etched much faster than the rest of the diamond. And it actually left just that loose octahedral core to move freely around inside the outer part of the octahedral diamond once the fibrous area was resorbed. So fascinating history. And as you can see from the sequence, it's pretty rare to have all these events come together just at the right time in the right way so that a diamond like this could form, which is why we don't see them very often. But there are 3 other examples that were that Emmanuel mentioned in this article that were actually previously documented in the literature that we know of already. Smaller diamonds. So.
Yeah, you know, these are exceptional specimens, aren't they? That shed light about unusual formation, of course, and processes, and we learn more about diamond growth and, of course, dissolution, which is really important. I mean, this is a great example here. We see these in many collections, these special shapes and unusual diamonds that we try and unravel how they grow. But when you apply this new mechanism, because we've got an exemplar example, you can almost say, well, this is how this formed. This is just a roof zone of one of these diamonds that shattered in effect, and what you're getting is a small piece of what was originally the original diamond that had grown in that formation.
Right. Yeah, so this stone on the left is shown in 2 different orientations. That's the same stone, and it's from the De Beers Special Collection. And you can actually infer a very similar growth mechanism and dissolution mechanism as we saw previously with the Mastroka diamond, where you had an OFO or octahedral, fibrous octahedral diamond that was, in this case, broken, and then the broken fragment was preferentially etched along that fibrous layer, leaving just the outer octahedral layer in this very unusual shape.
Yeah, amazing.
So by analogy,
actually, it might be a lot more common than you think, you know, because we might have the 3 great specimens, but these fragments might be the parts of many others.
Interesting to think about, yeah, that maybe these haven't even been recognized as much, but the fact that you could get a diamond that's not broken, but just has these dislocations that lead into the center and allows that core to move around inside, that's got to be pretty rare. So,
pretty cool, yeah, absolutely.
Yeah.
Okay, should we move on?
Yep.
Let's go to our gem notes. So we will quickly go through these. So this is a rare ruby showing an interesting sheen effect. 1.86 carats from Kenya, or reportedly Kenya anyway.
Yeah, and in this case, the ruby contains zones that were very intensely included by these iridescent platelets of hematite. And as the stone was moved in just the right orientation against the direction of the lighting, these would just light up and cause this interesting sheen effect in specific facets under the crown. The stone itself here looks a little orange, but the authors were confident it was a ruby. It's more of a orangey red variety, but it's a really interesting stone. Previously, they documented a more orangey sapphire that had the same effect, and it's similar to some of the so-called gold sheen sapphires that have reportedly come out of Kenya. And based on the chemistry of the sample, the authors also found that there were some similarities with gold sheen sapphires, so they may all be coming from the same deposit.
Same deposit, yeah, of course. Well, excellent. Then we go to an exceedingly rare mineral, Serendipit. This one is from, this mineral was named from the old Arabic for Sri Lanka, of course. This is a great spectroscopic study of Serendipit. It's quite a rare mineral. This is only 0.052 grams, 4.7 millimeters, but you can see the typical strong pleochroism from this vivid, like this greenish blue color, almost to colorless as well.
Yeah, and even though the sample was small, it still afforded a really good opportunity for research. And the authors had noted in the literature, there's not a lot of good Raman spectra of this mineral. And so they took the opportunity to do carefully oriented Raman spectrum of the sample, and they actually supplied all the data. So not only the spectrum, but the XY or raw data can be downloaded from the journal's data depository for people who want to add that to their own databases. And that's very helpful for being able to confidently identify this rare mineral if you're so lucky to encounter it.
Yeah. Moving on. Now this is an interesting one. Turquoise from Mongolia. Now we all know that turquoise is a copper aluminium phosphate, named from the Turkish, from Persian material. That's where it's really known for. Crystal is exceptionally rare, of course. It's triclinic, would you believe? And it usually occurs in these like nodular masses. But this is a really interesting one. For the standout thing for me was this great color, first off, for turquoise. And of course, this was a deposit that I think it's not been reported before. It was discovered in '64 in Mongolia, and then it's been mined since 1978.
So it's been known for quite a while, but for whatever reason, it hasn't been well characterized, at least in the English language literature. I think there's some Russian literature that documents it, but this is the first English language publication that I'm aware of that documents the gemological properties of this material. And it is quite nice. It doesn't need stabilization. That's the way it comes out of the ground. And it also has some interesting gemological characteristics. When you're characterizing it, normally you can get a nice Raman spectrum from turquoise, but in this case, only one particular laser, the 633 nanometer wavelength, was able to excite Raman spectrum that were useful for the identification. And for some reason, which we don't know at the time, the other lasers that were attempted, the 473 and the 532, just didn't produce usable Raman spectra. So it's an interesting reminder that sometimes it's important to try different lasers when you're analyzing a mineral by Raman spectroscopy, and not just for reasons of fluorescence, which is commonly what causes some problems with identifying minerals with Raman, for chromium-bearing minerals in particular. But in this case, it just didn't activate good spectrum unless you uses the correct wavelength of excitation.
Yeah, and I thought what's interesting for me also, when I was reading the paper, I always usually go to the geology bit first, actually. And you know, it's a supergene enrichment of an ore deposit, a copper deposit, and ground waters have filtered down through this thing and leached all the metals out, and then redeposited them into the enrichment zone. And this enrichment zone was like 100 meters thick. And you know, and that's all been mined out now. It says they're now down into the primary ore. So I do wonder whether there's not much of this material might be around if they've actually gone through that upper part of that deposit. So it'd be interesting to see.
Yeah, that's a good bet. Yeah.
Yeah. Okay. This is an eye opener, really. And when I first saw this, it was like, yeah, as in all gemology, it may be too good to be true. So this is the mollusks artificially filled with cultured pearls of various colors.
Just and you never know what you're going to encounter when you work in gemology. So it's just what keeps things interesting. This was material that's being sold on the online streaming market in China, where you have people who set up cameras and they go online and they say, you know, here we've got these mollusks that you can open yourself and pull out the pearls you find are yours. You know, you just buy the mollusks. So they send you the mollusks shrink wrapped in plastic, as you see on the left. And in this case, there were two different varieties that the authors obtained from this open market. There was a saltwater and a freshwater variety. And upon opening these, they found, as you see in photos B and C, there are pearls, unusually colored pearls that are not necessarily embedded in the tissue where you'd expect, but just kind of laying in the shell. And when they extracted they opened several of these different mollusks, they extracted those pearls shown on the bottom. And all they found through doing some spectroscopy, as well as just from looking at them, that all of the pearls except for the white ones on the right were dyed artificially. And not only that when you do X-ray imaging of these pearls, you find that they're all tissue nucleated freshwater cultured pearls. And so even though you have a saltwater mollusk, you've got a dyed freshwater cultured pearl, and clearly these pearls aren't coming from the mollusks that they're being sold in. So it's a bit deceptive.
Yeah, and I like the fact they threw the analytics at it again, but they did start off with the Gemmology, so they looked along, you know, residues in the cracks of the dye, and then on the surface reaching fractures, and any uneven coloration is what you would normally see, but the colours are so saturated, it's an immediate marker, isn't it?
Yeah.
And I think for us, when we spoke about it a few days ago, it's like, what must it be like? These things are shrink wrap, but when you open them, it might be a bit of a not very nice, even though they really, it's like they're for the consumers to personally collect their own pearls out of these.
Even if those pearls didn't come from there, that's
Yeah, that's right.
interesting.
Interesting. Good article.
Yeah.
Good note. So move on. This is really interesting. Now this HPHD grown near colorless synthetic diamond with detectable Gr1 defect. This is from the NGTC, I think, in China, that sees hundreds of thousands of diamonds go through their laboratories.
Yeah, this is a really unusual sample because in this case, it's a ring-mounted stone, weighs 1 carat, and it's got a very faint blue color. And when they did the analysis, it showed this small Gr1 defect, which normally is associated with natural stones. In this case, they were confident they were dealing with a synthetic stone because when they looked at the diamond view image, they found that there is the typical zoning, the cubooctahedral zoning that reflects synthetic origin. It's really hard to see on those diamond view images on the bottom because actually it was very hard to detect this zoning. It was very subtle the way
it's hazy, isn't it?
In the stone. Yeah, and it wasn't, the only way you could really see it was to look from the side, and with a ring-mounted stone, it's pretty difficult to see. When you look through the table, it was very, very subtle. So despite the fact that it had subtle zoning that showed it was synthetic, this Gr1 defect was something that was not expected. And so in the next slide, we'll see the spectra that were obtained from the stone. And here it's again, you have to really squint to see it, but on the right-hand side, on the bottom, on the far right spectrum, there's a little Gr1 peak at 741. And that is all that was shown that would tip off the authors about this. That shouldn't be there. But when you look at in combination with the other defects that were there, including radiation-related defects, it was all consistent with the fact that this diamond had been grown through HPHT methods and then experienced post-growth irradiation in the laboratory to perhaps even purposely introduce this defect to make it even harder to identify. So pretty sneaky.
Yeah, absolutely. And you know, they want to, whoever did this wanted to make it spectroscopically more natural, wasn't it? That's a really good note to put in there at the end of their summary. Yeah.
Yeah, exactly.
Okay, I think that's the notes we've done. Now I just want to move on before we take some questions. We do have an obituary section at the end of the journal, of course, and we're really sorry to show that Evelyn Stern passed away in just recently, aged 96 years old. And I did see in the obituary that she always looked younger than she appeared, and she did. She looked always younger, so I really was surprised at her age. But you know, Evelyn, FGA, of course, fellow of the Gemological Association. She was an international personality in diamonds and other things she did. She served on our board of trustees. She was the editor of the journal, the associate editor of the journal, Brendan, many times. Right. Yeah. And of course, she was examiner for our diamond diploma. And I just thought it fitting to end this webinar on the fact that, you know, we give our condolences, of course, to the family, but we'll sorely miss her because she had a great energy and capacity for life. She was always willing to talk to everyone, and she'll be sorely missed. Yeah. Okay, so of course, we're at the end of the seminar. Before we go to questions, how to access the journal, always good to point this out. If you become a member of GEMA for printed copies, of course, and online access to the most recent 2 years. But we do have an archive from 47 to 218. I urge you to look at that because there's some real great articles still relevant today, and not only for of course our learning, but to see how Gemology has progressed. That's really interesting. And it's easy to view on platforms, and of course it's downloadable. And there's a searchable index and subject bibliographies. I think you've just done a recent one, haven't you, Brendan? Because I downloaded it the other day and used it, so it's great.
Yeah, we just uploaded or just did an update, so it extends through 2020, and it's
all the way
very
through. Yeah, good job. And of course, don't forget the online data depository. There's more things in there, like additional photos, data clips, and some of the video clips we showed today are all there for you to look at. Okay. And thank you. And we welcome your feedback, of course. There's some things for email addresses, gemma.com, but education, membership, and instrument. So before we take questions, I'll just ask you, Brendan, quickly. Do you have any articles? You know, we see a lot of articles come through. Is there any articles you like to see in the future?
well. Yeah, I mean, it's part of being an editor of the journal is you rely on whatever kind of comes over the transom, and you can always send out feelers and requests for certain articles to various authors, but what you find is people are incredibly busy, and especially the people who are real experts in the field, they are so busy. But if I had a preference for certain articles, I mean, review articles are wonderful because they can compile a lot of data from the many different sources and put them all together into one place that can be really useful for people to refer back to. And they tend not to go out of date for many years as well. So review articles on instrumentation or certain techniques, diamonds, problems, colored stone issues. Also, I would say certain locality articles would be nice. It's interesting when you think about some of the important gem localities for colored stones in particular, like, for example, Ilakica in Madagascar. There's never been a full-length feature article that I know of on that locality, and
really?
it's still producing, and even though it's slowed down quite a bit. Tunduru, another example, never been a full-length feature article on Tunduru. So, I mean, these are Umba. I mean, these are all important areas that have produced a lot of stones for the trade and for many years. And it would be fascinating to see a nice article on those types of localities as well someday. And then finally, I think country-specific surveys of gem localities would be interesting. For example, if you were going to do an update, for example, on gem localities from Afghanistan, for example, there's a lot of changes happening in Ethiopia. You could do a gem survey article on all the localities that we know of there, what's come out, the qualities, the quantities, things like that. But again, getting this type of information is really difficult. So it's a bit of a pipe dream in this case.
Yeah. Okay, thanks. Yeah. Okay, I'm looking at my questions here. I've got one that says, is there any portions of the emeralds suitable for mineral specimens rather than cutting? And that's referring to Michael's article on Panjshir. So I suppose I could sort of take that one a bit in a way, because
Sure.
I've seen a lot of emerald mineral specimens on travels around various shows, and I think what's notable for me is that it all depends on the value. So when this material is found, if it can be cut into gems, a lot of it's broken pieces and fragments, not very carefully mined, and they will just cut them up into gems. But where you get a good crystal and the people who collect it know that it's a good crystal, it might actually be worth more as a emerald mineral specimen rather than a cut gemstone. And then it's got to find its way all the way to the right dealers to make that happen. But it really does depend on the material. And then this new material, the Type 2 stuff that's coming out, is such good quality that it would be exceptionally rare, I think, to find, a nice 3 or 4 centimeter crystalline matrix. But some of the images you see from many cutters' workshops is there are parcels of this material around that is cut. I'm amazed seeing the parcels of crystals that cutters have ready to cut, and I'm like, oof, I'd love to see the crystals just to see what they're like before they get cut into gemstones. Yeah. Okay, there's one for you, Brendan. How do you decide on the cover image of the journal?
Okay, well, that's an interesting question. Every one is different. What we do is we look at the content of the issue, the lineup of feature articles first, and look and see if those lend to being an attractive photograph of the material. And then if so, then I pursue a photo either with the authors of the article first, and if they can't supply a high quality image, then I will go to contacts in the trade and try to arrange to have one taken. So in almost all cases, these are photos that are custom made for the covers of those issues and not just existing photos that have already been around. And sometimes it can be pretty challenging to pull these together. So if we don't have a feature article that relates, then there's usually a gem note or something that will also lend itself well to a cover image. For example, the last issue, we had 2 beautiful rubies on the cover that came from a gem note that the AGL laboratory had submitted on some Burmese rubies that had beautiful inclusions inside.
Wow. Yeah. Interesting.
Yeah.
It's a badge of honor, isn't it? Getting the cover of the journal.
Absolutely.
Almost. Everyone wants the cover.
Yeah. Comes with a lot of cachet if you can get it. So.
Absolutely. Okay, we've got another question here. What is the geological setting of the Pangaea Type 2 deposit? Similar to Muso?
Well, the setting is actually similar in that they're both hydrothermal veins.
Yeah.
Muso is hosted by a black schist, or a black shale, I should say, and that black shale environment is relatively low metamorphism, so low pressure, low temperature type metamorphism that formed it. In Pangaea, you also have hydrothermal veins cutting metasedimentary rocks, but instead of black shales, there's carbonates and a variety of, there's schists, mica schist and things that have experienced a bit higher metamorphic grade. The veins themselves, though, are somewhat similar in that you have a series of carbonates like calcite, anchorite, and those are forming with quartz and some albite and things like this that all form in the veins together. And then once in a while, the veins will, open up and you'll get space for beautiful crystals to grow in that are clear gem quality crystals.
Yeah, I mean, in the article itself, they do go into the geology quite a bit, and it's quite amazing that Columbia and these Pangaea, they both have salinity, high salinity inclusions, don't they? Similar, obviously not exactly the same looking, but similar. So there were leaching of evaporite sequences, but Pangaea is a slightly higher temperature at 400 degrees.
Right.
It's an active mountain building area. Now that is one of the most active parts of the planet at the moment. And so the mountain building, they're quite relatively young as well, the age of them. So the Pangaea are about 23 million years old, I think. It's the age of crystallization, which in itself is mind-boggling, but yeah, it's a really interesting deposit.
Yeah, and like Columbia, there's no granite or pegmatite associated with the emerald mineralization, which is more common elsewhere, like in Zambia and Brazil, you have granites associated usually. So or some kind of pegmatite rocks.
Yeah. Okay. Well, I've got my note. It says we finished. Brendan, thank you so much for that.
Okay.
And congratulations on bringing out another journal. I know how much work it is to put these things together, but it's fantastic. And thanks to everyone for attending the webinar. We'll be making the recording available on our YouTube channel in due course. And of course, there you can see any of our previous webinars. You can find them on the same channel. And enjoy. So everyone, thanks for joining us. Have a nice evening, and we'll see you in a few months for number 6.
Sounds good. Thank you, everyone.
Bye, everyone.
Bye-bye.